All right, so here we go, normal distribution. Let's just start from the top. Before we can talk about normal distribution, let's talk about probability density functions. So previously we've talked about probability distributions, and that was specifically with discrete data. Now, and for the rest of the semester, we'll be talking about continuous data, specifically continuous random variables. So that's exactly what this is. This is a continuous random variable. So basically what this ends up being is this is an equation to show these random variables, because if you remember, right, a continuous random variable is one that goes on forever. So when we had discrete, right, discrete is countable. So that means that it's a finite number, right? Finite means there's a stopping place, right? You can count it. So all of our random variables were like 0, 1, 2, 3, and we could write out what their probabilities were off to the side. However, if you have a infinite amount, right? That's what continuous data is. Continuous is measurable, and thus it is infinite. And here's the reason why. If I, let's say that I, measured how tall I was. Well, I could say that I am 60 inches, right? But I mean, that's only one way that we could measure it. If you wanted to be a little more exact, you could be not just 60 inches, but 60.1 inches, or 60.00001 inches, or 60.00000000000000000000001 inches. And I think you might get my gist, right? You can kind of just keep on going forever. And so since there is literally, right, an infinite amount of numbers between just 60 and 61 inches. And because of that, there's no way to actually list them out like a probability distribution, right? So essentially what we're going to need to do is we're either going to need to have some sort of formula or equation, which we're not really going to talk more about that. We're going to talk about how to graph that equation. So don't worry too much about the equation itself. We're really going to be talking about this graph. So for a density function, this is this equation that we're going to be using. And when you graph it, what you end up seeing is that the total area under the graph of this equation, so when you actually graph it, the total area must equal to 1. The second thing is that the height of the graph of the equations must be at least 0. Right? So remember, that means 0 is the least it can be. No more or no less than 0. Good. So that is, the line must lie above or on the horizontal axis. So using these two parts of the definition, let's look at some examples. So example number 1. So let's determine if these three graphs are functions, or density functions. All right, so this is what we have so far. So we notice that it goes from 21, 22, 23, and the probability is 1/3, right? So this is our probability, and this is whatever we're talking about. That could be length, weight, whatever. So let's look at the first one. The first one said that it had to be the total area under the graph. So if we look at this, what does this look like? What shape did I draw? I drew a square or a rectangle, right? Probably a rectangle would be the better way of explaining it. Good. So how do we find the area of a rectangle? Well, for those of us who might remember it is the length times the width, right? So we have length times width, or base times height. Might be another thing you've heard. Good. So what is the length of this? Well, if we see how many numbers is between 21 to 23, what'd you have to add to it? Well, it's 2, right? So the length is 2. What's the width? We see it's 1/3, right, from right here. So 2 times 1/3 is 2/3. So the area is 2/3. But what did we say that the area had to be? What was the first one? It has to be 1. So is this a density function? No, it is not. Good, and we can just write that. No, because the area does not equal 1, right? It equals 2/3. Let's look at the second one. So what about this? So, again, we have 3 different rectangles, so we can kind of figure out the area of each of them and then add them all together. So the first one, we see the width is 1 and the height is 1. So 1 times 1 is just 1. So this area is 1. This one, once again, the width is the length is 1. The width this time is -1, right? Because it's going from positive to negative. So when we multiply these two together, we end up with -1. And then once again, we have the length, which is 1, the width, which is 1. 1 times 1 is 1. So when we add all these together, what do we get for the area? We get 1 plus -1 plus 1. These two cancel out to get 0, so we end up with just 1. So the area actually is perfect. So let's look at the second part of that equation. Second part of the, not equation, the definition. So the height must be at least 0, aka the graph has to lie on or above the horizontal axis. So is that true in this case? No, right? Because we see right here, there's a negative height. Right? It goes below this horizontal axis. So we can say no, because the graph falls under the horizontal axis. Right? So that can be an example. You could also say something like, no, because we have negative height. And that's not possible, right? It has to be 0 or above. Good. All right, let's look at one more. So let's look at this one. So is this a probability distribution? So looking at our 2 parts of the definition, we know the area has to equal 1. So does the area equal 1? Well, if we look at the length, right? How far apart are these? These are 2, right? So the length is 2. What's the width? 1/2. We know that 2 times 1/2. What's half of 2? Oh, hold on a second. Something happened. There we go. It's 1. So area is 1. Good. Second one. Is the height of each of them greater than or equal to 0? Yeah. The height's actually right here. It's at 1/2. Right? And anything beyond that is just at 0. Good. So is this a probability distribution? Yes, it is. Yeah, it doesn't say anything about what the actual data is, right? These could be negative. We could talk about this might be degrees Celsius, right? You could have a negative degrees Celsius. That makes sense. Good. All right. So hopefully we're feeling okay with this. Let's look at another example. So here's a uniform distribution. Remember, uniform means everything has the same probability. So this is about voltage. So these are all in volts. So the question first is this graph an example of a probability or density function? So first part, we got total area. Area needs to equal 1. So what is the area? So we're going from 123 to 125. So we see that's actually 2. This is sectioned off into 0.5s. So it's a little different. You make sure to pay attention to that kind of stuff. The width is 1/2. Well, we already showed that 2 times 1/2 is 1. Oh, there we go, is 1. So that part's good. Second part, are all the heights greater than or equal to 0? Yep, absolutely. So yes. So this is a probability density function. Good. All right. So let's go back because we need to finish some notes that we've talked about. So because the total area under the curve is equal to 1, right? We said the total area under that curve is 1, and the total probabilities for all outcomes. So if you have all of the outcomes, right, what would be the probability of all of them together, the total probabilities? If you add them all together, you should end up with 1, right? We talked about that a couple of times now. So, right, since the area under the curve is 1 and the probability is 1, right, and the second thing, we know there has to be at least 0, right? So essentially you end up with something between 0 and 1. This is starting to sound like area and probability can basically just be interchangeable. So now, if you are trying to determine, you can determine the area under this curve to find the probability. So basically, you can interchange area and probability from now on. If we say find the probability, and it's something like a density function, you can actually just find the area. So going back to our example, right? Find the probability that a randomly selected voltage is greater than 124.5 volts. So let's erase all this for a second. So where's 124.5 on this graph? We see that it's here. And basically, do we want everything to the left of it or to the right of it? Well, it says greater than, so we want everything to the right of it. So we can just shade in all of this. So this is the area. Whoop, disappeared on me. This is, nope, disappeared again. Let's try to see if we can. Oh, that's not doing great. There we go. All right. Cool, cool, cool. All right, so we have the area. So to find the probability, remember we said probability and area are the same thing. So we can just figure out what is this area. And we already know how to do area, right? It's length times width. So we can see that between 124.5 and 125, we get 0.5. And we see that the width, once again, is 0.5 because 1/2 is 0.5. So 0.5 times 0.5 is just 0.25. Right? 25%, which also makes sense, right? We could kind of cut this up into 4 different sections, and this would be one of the 4, which would be 25%. Now, find the probability that a randomly selected voltage level is less than 123.75 volts. So, if you look at the 123.75, that will be right between 123.5 and 124.0. So right here, we got 123.75. And do we want to shade everything to the left of it or to the right of it? Well, it says less than, so that's going to be to the left. Good. So this is everything we want. So what's going to be the width, or the length, excuse me. The length, right, from 123.0 to 123.75 is just 0.75. The width, again, is just 0.5. So we do 0.75 times 0.5, and it's all disappearing on me again. I don't know what's happening. There we go. Which is 0.375. Okay. Good. Also, another way that we could do this, another way we could write this out. You could say, right, the probability of any random variable, right? You want to randomly select it, so any random variable being greater than 124.5. And that's going to be annoying. All right. So this is another way to write that. So if you saw something like this, that's all it's saying. What's the probability, right? That's what the P means, of a variable being greater than 124.5. All right, we can do the same thing. So let's the probability less than 123.75. So we have less than 123.75. So again, this is just kind of notation. You don't necessarily need to know how to write it, but you should be able to identify it, right? So if I wrote this for you, you should be able to read this. And then for the last one, what's the probability that we have a voltage level between 123.36 and 124.94? So we could write that as the probability of X being between 123.36 and 124.94. Yeah, we're definitely going to have to pause this video after we finish this example because this is not going to be working for the rest of the video. All right, so we can just go up to our graph. So erase all this stuff. So we see that we are at 123.36, which is somewhere around here, and 124.94, which is going to be somewhere around here. And so we want between, so we just shade everything in between. All right. So what's the length? So if we see, right, we can just kind of subtract 124.94 minus 123.36. And when we subtract, we get 1.58 as our length. 0.5 is once again our width. So we do 1.58 times 0.5. You end up with 0.79, which is our answer. All right, I don't know what's happening with this video, so I'm gonna pause it and I'll do a part 2 after I figure out what everything, after I fix everything. But make sure to watch the part 2 as well.